galaxies, those magnificent islands of stars, dust, and dark matter, have held a profound and enduring grip on the human imagination for centuries. From the faint, milky smudge of our own galaxy arching across a dark night sky to the stunning, detailed portraits of distant spirals captured by our most powerful telescopes. They are the grand architectural pillars of the cosmos. At first glance, they might seem like isolated, self-contained entities, marbles of light scattered across the vast, dark expanse of space. We see the elegant, pinwheeling arms of spiral galaxies, the serene, golden glow of elliptical giants, and the chaotic, misshapen forms of irregulars, hinting at a history of violent, cosmic collisions. But this picture of isolation is a profound illusion. These galactic structures are not solitary islands. They are the luminous nodes in a vast, interconnected tapestry that weaves the entire universe together. This is the cosmic web, an immense and intricate network of filaments stretching for billions of light years across the cosmos, a celestial superhighway of matter and energy. At the intersections of these filaments, we find the great galaxy clusters, the bustling metropolises of the universe. The filaments themselves are the cosmic byways, trails of galaxies and intergalactic gas that connect these clusters, while the vast, seemingly empty voids in between are the silent, dark countrysides. The very existence of this cosmic web raises a host of deep and fundamental questions. Why do galaxies cluster along these specific, filamentary structures? What invisible forces guide the flow of matter across the immense voids? The answers, we are learning, lie beyond the realm of the visible. They lead us into the domain of the unseen, the mysterious, and the profoundly powerful. The grand architectural scaffolding of the cosmic web is not built from the stars and gas we can see. It is shaped by a mysterious and invisible substance known as dark matter. This enigmatic entity, which we cannot see or touch, which does not emit, absorb, or reflect any form of light, is the silent, gravitational majority of the universe, outweighing all the normal, baryonic matter by a factor of more than 5 to 1. It is the unseen hand that has guided the formation of every galaxy, every cluster, every filament in the cosmos. But dark matter is not the only invisible force at play. Looming at the heart of almost every massive galaxy is a supermassive black hole, a region of space-time where gravity is so intense that nothing, not even light, can escape. These are not passive, cosmic drains, silently swallowing matter. They are dynamic and powerful engines, their immense gravitational pull dictating the orbits of billions of stars, and their ferocious, high-energy outbursts of radiation and particles regulating the very process of star formation within their host galaxies. They are a profound paradox, a point of ultimate destruction that is also a key agent of cosmic order and creation. And the cosmic drama does not end with these internal forces. Galaxies are social creatures. They are constantly interacting, their immense gravitational fields reaching out across millions of light years to pull on their neighbors. These interactions can be subtle, a gentle tidal stripping of a small satellite galaxy by its massive host, or they can be cataclysmic, a head-on collision between two spiral galaxies of equal size. These major mergers are some of the most spectacular and transformative events in the universe. Cosmic dances of creation and destruction that unfold over hundreds of millions of years. As the two galaxies collide, their vast clouds of interstellar gas are compressed, triggering a furious burst of star formation. A starburst that can briefly outshine all the other stars in the galaxy combined. The elegant spiral structures are torn apart, their stars flung into long tidal tails, and eventually the two galaxies will merge into a single, larger, and often elliptical galaxy. These collisions are a primary driver of galactic evolution, shaping the size, the structure, and the destiny of the galaxies we see today. But even as we begin to understand this intricate dance of dark matter, black holes, and galactic collisions, we are confronted with an even deeper and more pervasive mystery, the existence of dark energy. This is a strange, repulsive force, a property of space itself, that is causing the expansion of the entire universe to accelerate. While its existence is now well established by our observations, its fundamental nature remains a complete enigma. Is it a constant, unchanging property of the vacuum, or is it a dynamic entity whose strength changes over cosmic time? The answer to this question will determine the ultimate fate of our universe, and the ultimate fate of the very galaxies we are trying to understand. And then there is the most profound question of all, the question that underlies all of our cosmological inquiries. Why does the universe exist in this particular form? Could it have been different? Are there other parallel realities? Other universes where the laws of physics are different, where galaxies formed in a completely different way? Or perhaps where they never formed at all? These are the grand, open-ended puzzles that fuel the relentless, passionate curiosity of astronomers, physicists, and cosmologists. Every star, every orbit, every galactic spin is a thread in the cosmic tapestry, a clue in a detective story that is billions of years in the making. Today, we begin to pull on some of these threads, to peel back the cosmic veil, and to explore the forces, the entities, and the enigmas that have shaped the magnificent galactic islands we call home. The story of galaxy formation begins not with stars or gas, but in the fiery, primordial crucible of the Big Bang itself. This is the moment, some 13.8 billion years ago, when not just matter and energy, but space and time themselves exploded into being. The popular image of the Big Bang as an explosion in space is a misleading one. It was an expansion of space, an event that happened everywhere at once, in the first infinitesimal fractions of a second. The universe was an unimaginably hot and dense singularity, a point of infinite temperature and density where our current laws of physics break down. This was followed by a period of astonishing, hyper-accelerated expansion known as cosmic inflation, a process that stretched the nascent universe from a subatomic size to something larger than a grapefruit in a time far shorter than the blink of an eye. As this inflationary period ended, its immense energy was converted into a hot, dense soup of fundamental particles. This was the true beginning of the hot Big Bang phase. At these extreme temperatures, well into the trillions of degrees, the familiar particles of our world could not exist. The universe was a quark-gluon plasma, a chaotic, seething sea of the most fundamental building blocks of matter quarks and the gluons that bind them along with photons, electrons, and other elementary particles. As the universe continued to expand and cool, it passed through a series of critical phase transitions. After about 1 microsecond, the temperature had dropped enough for the quarks and gluons to freeze out, combining in groups of 3 to form the first protons and neutrons, the building blocks of atomic nuclei. This was a pivotal moment, but it was also a moment of profound and enduring mystery. The laws of physics, as we understand them, are almost perfectly symmetric with respect to matter and antimatter. For every type of particle, there should be an antiparticle with the same mass but opposite charge. In the intense heat of the early universe, particles and antiparticles should have been created in equal amounts. And when a particle meets its antiparticle, they annihilate each other in a burst of pure energy. This means that as the universe cooled, almost all the matter and antimatter should have annihilated, leaving behind a universe filled with nothing but a diffuse bath of radiation. But this is not what we see. We live in a universe that is made almost entirely of matter. For every billion antiparticles in the early universe, there must have been 1,000,000,001 particles of matter. This tiny 1 in a billion imbalance. This slight preference of the universe for matter over antimatter is the reason that we exist. The process that created this imbalance is known as baryogenesis, and its precise mechanism remains one of the great unsolved puzzles in modern physics. It is a mystery that is deeply connected to the fundamental symmetries of nature, and its solution will likely require a new physics beyond our current standard model. As the universe continued its journey of cooling and expansion, it entered the next crucial phase of its early evolution, Big Bang nucleosynthesis. Between about 1 and 3 minutes after the Big Bang, the temperature had dropped to a mere billion degrees, cool enough for the protons and neutrons to begin to fuse together. Forming the nuclei of the first light elements, the universe became a primordial nuclear reactor. Protons and neutrons combined to form deuterium, which then fused to form helium-4, along with trace amounts of helium-3, lithium, and beryllium. This process was incredibly efficient, but also very short-lived. After about 20 minutes, the universe had expanded and cooled to the point where nuclear fusion was no longer possible. The result was a universe whose baryonic matter was composed of about 75% hydrogen nuclei, 25% helium nuclei, and a tiny fraction of lithium. The precise predictions of Big Bang nucleosynthesis for the abundances of these light elements are one of the great triumphs of the Big Bang model, matching our observational measurements with stunning accuracy. But for the next 380,000 years, the universe remained a hot, dense, and opaque plasma. The temperature was still too high for the newly formed atomic nuclei to capture the free-roaming electrons. This sea of free electrons acted like a dense fog, constantly scattering the photons of light and preventing them from traveling any significant distance. The universe was a glowing but impenetrable haze. Then, as the universe reached the age of 380,000 years, it crossed another critical threshold. The temperature dropped to about 3,000 Kelvin, cool enough for the electrons to finally be captured by the atomic nuclei, forming the first stable, neutral atoms. This event is known as recombination or decoupling. Suddenly, the cosmic fog lifted. The universe became transparent to light. The photons that had been trapped in the primordial plasma were now free to travel unimpeded through the expanding space, and they have been traveling ever since. Their wavelength stretched by the subsequent expansion of the universe from the high-energy light of a glowing fireball into the cool, faint microwaves that we detect today from all directions in the sky. This is the cosmic microwave background, the oldest light in the universe, a beautiful and incredibly informative fossil of the infant cosmos. The CMB is not perfectly uniform. It contains tiny, almost imperceptible temperature fluctuations, variations of about 1 part in 100,000. These tiny anisotropies are the imprints of the initial density fluctuations in the primordial universe, the quantum ripples from the inflationary epoch that were stretched to astronomical scales. These fluctuations are the seeds of all cosmic structure. The slightly denser regions were the gravitational wells into which matter would later fall, the birthplaces of the first stars and galaxies. The slightly less dense regions would become the great cosmic voids. The CMB is a baby picture of our universe, a snapshot of the moment it first became transparent, a map of the primordial seeds from which the entire, glorious and complex tapestry of the cosmos would eventually grow. The period following the release of the cosmic microwave background, from about 400,000 years to a few 100 million years after the Big Bang, is known as the cosmic dark ages. The universe was now transparent, but it was also dark. The primordial fireball had faded, and there were not yet any stars or galaxies to light up the cosmos. The universe was a vast, expanding, and slowly cooling expanse of neutral hydrogen and helium gas, with the tiny primordial density fluctuations sown by inflation gently growing under the influence of gravity. The Dark Ages were a time of quiet gestation, a period where the seeds of cosmic structure were slowly, patiently beginning to sprout. In the slightly denser regions of the universe, gravity began to win its long battle against the outward pressure of the gas. The neutral hydrogen and helium began to clump together, forming vast, filamentary structures, the first skeletal outlines of the cosmic web. The dominant gravitational player in this process was not the normal, baryonic matter, but the mysterious, invisible dark matter. Because dark matter does not interact with light, it was not coupled to the radiation pressure of the early universe. It was free to begin clumping and forming gravitational halos long before the baryonic matter. These dark matter halos acted as the gravitational seeds, the cosmic nurseries into which the normal gas would later fall. Over millions of years, the gas within these dark matter halos became denser and denser. As it was compressed, it began to heat up. But for a star to form, the gas must be able to cool, to radiate away its heat, so that gravity can continue its work of compression. The primordial gas of the Dark Ages, composed almost entirely of hydrogen and helium, was a very inefficient coolant. It took a long time and a lot of mass for a gas cloud to cool enough to trigger the first star formation. But eventually, in the densest hearts of the most massive of these early dark matter halos, the conditions became right. The first stars were born. The ignition of these first stars, known as Population 3 stars, marks the end of the cosmic Dark Ages and the beginning of the cosmic dawn. These were not like the stars we see today because they formed from the pristine, metal-free gas of the early universe. They were incredibly massive, perhaps hundreds of times the mass of our Sun. And because of their immense mass, they were incredibly hot, incredibly luminous, and incredibly short-lived. They blazed with a fierce, blue-white light, flooding the surrounding darkness with the first starlight the universe had ever known. Their intense, high-energy ultraviolet radiation began to ionize the neutral hydrogen gas around them, creating expanding bubbles of ionized plasma in the surrounding dark. And their lives ended in spectacular, cataclysmic supernova explosions that seeded the universe with the first heavy elements, the metals that would be essential for the formation of the next generation of stars, of planets, and of life itself. These first stars were the pioneers, the cosmic trailblazers who lit up the darkness and began the long, complex process of transforming the simple, primordial universe into the rich, chemically diverse, and life-bearing cosmos we inhabit today. The birth of the first stars triggered a cascade of structure formation in the early universe. The dark matter halos that hosted these stars continued to grow, merging with their neighbors to form larger and larger structures. Within these halos, the gas, now enriched with the first heavy elements from the Population 3 supernovae, could cool more efficiently, leading to the formation of the first protogalaxies. These were small, irregular, and chaotic systems, a far cry from the grand, ordered spiral galaxies we see today. They were the building blocks, the cosmic Legos, from which the larger galaxies would be assembled over billions of years. This is the hierarchical or bottom-up model of galaxy formation, the current standard paradigm in cosmology. In this picture, small things form first, and then merge to form bigger things. The early universe was a violent and dynamic place, a cosmic construction site where these proto-galaxies were constantly colliding and merging, triggering intense bursts of star formation. The James Webb Space Telescope has given us our first tantalizing glimpses into this chaotic early epoch. It has observed galaxies that were already in place just a few 100 million years after the Big Bang. Their light red shifted into the infrared by the expansion of the universe. And these early galaxies are not always the small, messy objects our models predicted. Some of them appear to be surprisingly large, surprisingly massive, and surprisingly well organized, challenging our understanding of how quickly these structures could have formed. As these first proto-galaxies grew and evolved, their combined radiation, along with the radiation from the first quasars, began to have a profound impact on the universe as a whole. This was the epoch of reionization. The bubbles of ionized hydrogen created by the first stars and galaxies began to grow and overlap, until, by about 1 billion years after the Big Bang, the entire vast expanse of the intergalactic medium had been transformed from a cold, neutral gas back into a hot, ionized plasma. The universe, which had been dark and opaque during the Dark Ages, was now transparent and filled with light once again. This was a fundamental phase transition for the cosmos, a second coming of age that set the stage for the evolution of the large-scale structures we see today. The epoch of reionization was not a simple, uniform process. It was a patchy, complex affair, with some regions of the universe becoming ionized earlier than others, depending on the local density of stars and galaxies. Mapping this process in detail is one of the primary goals of modern cosmology, as it holds the key to understanding the nature of the first luminous sources and their impact on the cosmic environment. Observatories like the Square Kilometre Array are designed to detect the faint, 21-centimeter radio signal from the neutral hydrogen of the Dark Ages and the epoch of reionization, which will allow us to create a three-dimensional map of this crucial transformative period in our universe's history. The story of the first stars and galaxies is a story of how, from the quiet darkness of a simple primordial state, the first points of light emerged, and how that light, in turn, transformed the entire cosmos, setting the stage for the rich, complex, and beautiful universe we now inhabit. It is a story of how the universe lit its own fire, a fire that continues to burn in the hearts of billions of galaxies, including our own. The galaxies we see in the universe today are not a random assortment of shapes and sizes. They fall into a surprisingly well-ordered classification scheme, a tuning fork diagram first developed by the great astronomer Edwin Hubble in 1926. This scheme, which is still the starting point for our understanding of galaxy morphology, divides galaxies into three main classes: ellipticals, spirals, and irregulars. Elliptical galaxies are smooth, featureless, and often spheroidal or football-shaped collections of stars. They are the old red and dead galaxies of the universe. They are dominated by old reddish stars. They contain very little cold gas and dust, and they have very low rates of ongoing star formation. They are the calm, stately, and retired citizens of the cosmic city. Spiral galaxies, like our own Milky Way, are the vibrant, active, and youthful members of the galactic population. They are characterized by a flat, rotating disk of stars, gas, and dust, with beautiful, elegant spiral arms where new, hot blue stars are constantly being born. They often have a central, spheroidal bulge of older stars, and many, including our own galaxy, have a central bar-like structure from which the spiral arms emerge. These are the barred spiral galaxies. Irregular galaxies, as their name suggests, are the misfits, the rebels of the cosmic zoo. They lack any clear, defined structure. They are often chaotic, clumpy, and rich in gas and dust, with high rates of vigorous and often bursty. Star formation. They are the cosmic works in progress, galaxies that are still in the process of being assembled or have recently been disturbed by a close encounter with a neighbor. The Hubble tuning fork is not just a classification scheme. It is also, in a rough sense, an evolutionary sequence. The current paradigm of galaxy formation, the hierarchical model, suggests that the chaotic, irregular galaxies of the early universe gradually, through a series of mergers and a long period of more quiescent evolution, transform into the grand and ordered spiral and elliptical galaxies we see today. The key driver of this transformation is gravity, which pulls together the dark matter halos, which in turn pull together the gas and the stars. But the story is not just one of gravity. It is a complex interplay of a host of different physical processes, a cosmic dance of feedback and regulation. The process of star formation itself is a powerful feedback mechanism. The intense radiation and powerful stellar winds from young, massive stars can heat and blow away the surrounding gas, inhibiting the formation of further stars. The supernova explosions that mark the end of these massive stars' lives are even more powerful. They inject a huge amount of energy and heavy elements into the interstellar medium, creating vast, expanding superbubbles of hot gas that can clear out entire regions of a galaxy, temporarily shutting down star formation. But this feedback is not just destructive. The shock waves from these supernovae can also compress the surrounding gas clouds, triggering a new wave of star formation. It is a self-regulating cycle of birth, death, and rebirth. On an even larger scale, the supermassive black holes at the centers of galaxies are now known to be crucial players in this cosmic feedback loop. As gas falls towards the central black hole, it forms a hot, luminous accretion disk, which can launch powerful jets and winds that can travel at nearly the speed of light. This active galactic nucleus feedback can be so powerful that it can heat and expel the gas from the entire galaxy, effectively quenching all future star formation. This is thought to be the primary mechanism that transforms large, star-forming spiral galaxies into quiescent, red and dead elliptical galaxies. The beautiful, ordered structures we see in the universe today are not a static, final state. They are the product of a long, violent, and complex history. A history of mergers, of starbursts, of feedback, of a constant, dynamic interplay between the creative force of gravity and the regulatory forces of stellar and AGN feedback. The universe is not just a collection of galaxies. It is a dynamic, evolving ecosystem, and understanding the intricate feedback loops that govern this ecosystem is one of the central goals of modern astrophysics. The evolution of a galaxy is not just determined by its internal processes. It is also profoundly shaped by its environment. A galaxy that lives a solitary life in the middle of a cosmic void will have a very different history from a galaxy that inhabits the dense, crowded heart of a massive galaxy cluster. This is the nature versus nurture debate of cosmology. The nature of a galaxy is its intrinsic properties, like its mass and its angular momentum, which are largely determined by the initial conditions of the dark matter halo in which it formed. The nurture is the influence of its environment, the interactions with its neighbors, and with the larger cosmic web. Both are crucial. An isolated galaxy, a cosmic hermit, can evolve in a relatively peaceful and quiescent way. It can slowly accrete gas from the surrounding intergalactic medium, fueling a steady, long-lived rate of star formation. This is the likely history of many of the beautiful, grand-designed spiral galaxies we see in the field. But a galaxy that lives in a dense cluster is subject to a host of environmental processes that can dramatically alter its fate. As a galaxy falls into a cluster, it moves through the hot, dense intracluster medium, the tenuous gas that fills the space between the cluster galaxies. This can lead to ram pressure stripping, where the galaxy's own interstellar gas is stripped away by its motion through the intracluster medium, like a runner's hair being blown back by the wind. This process can quickly remove a galaxy's fuel for star formation, transforming a blue, star-forming spiral into a red quiescent S0 or lenticular galaxy. Galaxies in clusters are also subject to more frequent gravitational interactions. Tidal stripping can occur when a smaller galaxy passes close to a larger one, its outer stars and gas being torn away by the stronger gravitational pull of its massive neighbor. We see evidence of this in the long, beautiful tidal streams of stars that are often seen snaking around massive galaxies like our own Milky Way and the Andromeda Galaxy. These streams are the ghostly remnants of dwarf galaxies that have been tidally disrupted and are in the process of being accreted. And of course, there are the direct cataclysmic collisions and mergers. While these are more common in smaller galaxy groups, they can also occur in clusters, leading to the formation of the most massive galaxies in the universe. The giant CD elliptical galaxies that are often found at the very center of rich clusters. These cosmic behemoths are thought to be the product of multiple, repeated mergers over cosmic time. The environment of a galaxy, therefore, plays a pivotal role in its evolution, in a process that is sometimes called galaxy harassment. The dense, violent, and gas-poor environment of a cluster tends to transform star-forming spiral galaxies into quiescent elliptical and S0 galaxies. This is known as the morphology-density relation, a well-observed correlation in the local universe. The cosmic web itself plays a crucial role in this environmental story. The filaments of the web act as the cosmic highways along which galaxies and gas are funneled into the growing clusters at the nodes. Galaxies that live in the filaments are in a transitional environment, still accreting gas and forming stars, but also beginning to feel the gravitational influence of the nearby cluster. They are the suburban galaxies, on their way to the bustling and often brutal life of the cosmic city. Understanding the complex interplay between a galaxy's intrinsic nature and its environmental nurture is one of the key challenges in building a complete picture of galaxy formation and evolution. It requires a combination of large-scale cosmological simulations that can model the growth of the cosmic web and the formation of clusters, and high-resolution zoom-in simulations that can model the detailed, messy physics of star formation, feedback, and galactic interactions within individual galaxies. It is a monumental task, but it is one that is bringing us closer than ever to a complete and beautifully complex understanding of the origin and evolution of the magnificent star islands that we call home. Our own cosmic home, the Milky Way Galaxy, and its nearest major neighbor, the Andromeda Galaxy, provide us with a unique and powerful laboratory for studying the processes of galaxy formation and evolution up close. They are the two largest members of the local group, a gravitationally bound collection of more than 50 galaxies, and they offer us a detailed archaeological window into the history of a typical large spiral galaxy. The Milky Way is a barred spiral galaxy, a vast rotating disk of about 100 billion stars, with a central bar-like structure and a number of spiral arms. We are located in one of these arms, the Orion Arm, about 27,000 light-years from the galactic center. By meticulously mapping the positions, motions, and chemical compositions of the stars in our galaxy, a field known as galactic archaeology, astronomers are able to piece together the story of its formation. We have learned that the Milky Way, like other large galaxies, was built up over billions of years through the hierarchical merger of smaller protogalactic fragments. The oldest stars in our galaxy are found in its stellar halo, a vast, diffuse, and spherical component that surrounds the disk, and in its central bulge. These stars are typically metal-poor, meaning they have a low abundance of elements heavier than hydrogen and helium. a sign that they formed early in the universe's history, before many generations of stars had had a chance to enrich the interstellar medium. The disk of the galaxy, on the other hand, is home to younger, more metal-rich stars, like our own Sun, and is the site of most of the ongoing star formation. The evidence for the Milky Way's merger history is written in the sky. We see numerous stellar streams, long, coherent trails of stars that are the tidally disrupted remnants of smaller dwarf galaxies that have been, or are currently being, accreted by our own. The Sagittarius Stream, for example, is a vast river of stars that wraps around the entire galaxy, the ghost of a dwarf galaxy that is being torn apart by the Milky Way's immense gravitational pull. These streams are the fossils of our galaxy's cannibalistic past, and by studying their orbits and their stellar populations, we can reconstruct the timeline of our galaxy's assembly. The Andromeda Galaxy, also known as Messier 31, is our cosmic twin, a slightly larger spiral galaxy located about 2.5 million light-years away. It is the most distant object that can be seen with the naked eye, a faint, fuzzy patch in the night sky, and it is on a collision course with our own. In about 4.5 billion years, the Milky Way and Andromeda will begin a long, slow, and spectacular merger, a cosmic dance that will, over hundreds of millions of years, transform the two spiral galaxies into a single, massive elliptical galaxy, which some have nicknamed Milkomeda. This future collision provides us with a real-time preview of one of the most important processes in galaxy evolution. But Andromeda also offers us a unique, external perspective on a galaxy that is very similar to our own, because we see it from the outside. We can study its overall structure, its spiral arms, its stellar halo, in a way that is difficult for our own dust-obscured galaxy. Observations of Andromeda have revealed a history that is remarkably similar to our own, with a vast stellar halo filled with the remnants of past mergers and a complex, clumpy disk that is still actively forming stars. The study of the local group, with its two giant spirals and its retinue of smaller, dwarf satellite galaxies, is a field that is rich with information about the processes of galaxy formation, of feedback, of tidal stripping, of mergers. It is our own local cosmic ecosystem, and by studying it in detail, with telescopes like Gaia, which is mapping the positions and motions of 1 billion stars in our galaxy, and the James Webb Space Telescope, which can peer through the dust to see the individual stars in Andromeda. We are piecing together the story of our own cosmic origins, a story that is both uniquely our own and also a beautiful and representative chapter in the grand universal epic of galaxy formation and evolution. The luminous baryonic matter that makes up the stars and gas of galaxies is only a small fraction of the total cosmic inventory. The vast majority of the matter in the universe, about 85% of it, is in the form of dark matter, a mysterious, invisible substance that does not interact with light. The story of galaxy formation is, in a very real sense, the story of dark matter. It is the dark matter that provides the gravitational scaffolding, the invisible architecture upon which the visible structures of the universe are built. The existence of dark matter was first inferred in the 1930s by the Swiss astronomer Fritz Zwicky, who observed that the galaxies in the Coma cluster were moving far too fast to be held together by the gravity of the visible matter alone. He postulated the existence of some form of Dunkel materia, or dark matter, to provide the extra gravitational glue. His idea was largely ignored for decades, until the 1970s, when the astronomer Vera Rubin made a similar discovery on the scale of individual galaxies. She meticulously measured the rotation curves of spiral galaxies, the speed at which the stars orbit the galactic center as a function of their distance. According to Newtonian gravity, the stars at the outer edges of a galaxy, where the visible matter thins out, should be moving much more slowly than the stars in the inner regions. But Rubin found that the rotation curves were flat. The outer stars were moving just as fast as the inner ones. This was a stunning result, and it provided the most compelling evidence yet for the existence of a vast, extended halo of invisible dark matter surrounding the visible disk of the galaxy. A halo whose gravitational pull was responsible for the high orbital speeds of the outer stars. Since then, the evidence for dark matter has become overwhelming. We see its effects in the gravitational lensing of distant objects by galaxy clusters, in the temperature fluctuations of the cosmic microwave background, and in the very existence of the large-scale structure of the universe. The cosmic web itself is primarily a web of dark matter. The standard model of cosmology is now the lambda cold dark matter model, where cold dark matter is the specific type of dark matter that is thought to make up the bulk of the universe's mass. Cold in this context means that the dark matter particles were moving slowly in the early universe, which allows them to clump together easily and form the small-scale structures, the dark matter halos that are the seeds of galaxy formation. The story of galaxy formation, then, begins with the dark matter. In the early universe, the tiny quantum fluctuations from inflation created small overdensities in the otherwise uniform distribution of dark matter. These overdensities began to grow under the influence of their own gravity, collapsing to form the first small dark matter halos. This is a hierarchical, bottom-up process. Small halos form first, and then, over cosmic time, they merge to form larger and larger halos. The normal baryonic matter is, at first, just a passive bystander in this process. But after the universe becomes transparent at the time of recombination, the baryonic gas is free to fall into the deep gravitational potential wells of these pre-existing dark matter halos. It is within these dark matter cocoons that the gas can cool, condense, and form the first stars and galaxies. The properties of a galaxy, its mass, its size, its shape, are thought to be largely determined by the properties of the dark matter halo in which it resides. The distribution of dark matter is not just a passive scaffolding. It is the genetic code that dictates the form and evolution of the visible galaxy. While the LCDM model has been remarkably successful in explaining the large-scale structure of the universe, it does face some challenges on smaller, galactic scales. The cusp core problem. The fact that the centers of some dark matter halos appear to be less dense than the cuspy profiles predicted by simple CDM simulations. And the missing satellites problem. The fact that we observe fewer small, dwarf satellite galaxies around the Milky Way than the simulations predict have led some to question the simple, collisionless nature of cold dark matter. These small-scale crises may be solved by a more sophisticated understanding of the messy baryonic physics of feedback, which can heat and expel matter from the centers of galaxies. Or they may be a hint that the nature of dark matter is more complex than we think. Perhaps dark matter is self-interacting, or warm, or has some other exotic property. The quest to identify the dark matter particle is one of the most urgent and exciting challenges in all of modern science. Experiments deep underground are trying to detect the faint, rare interactions of dark matter particles with normal matter. Particle accelerators like the Large Hadron Collider are trying to create dark matter particles in high-energy collisions, and telescopes are searching for the indirect signatures of dark matter annihilation in the gamma-ray sky. The mystery of dark matter is a puzzle that connects the largest structures in the cosmos with the smallest, most fundamental constituents of reality, and solving it will be a crucial step in completing our picture of how the magnificent islands of stars we call galaxies came to be. The story of galaxy formation and evolution is a story of immense complexity, a story that plays out over billions of years and involves a delicate and intricate interplay of gravity, gas dynamics, star formation, stellar feedback, black hole activity, and the mysterious influences of dark matter and dark energy. To understand this complex, multi-scale process, astronomers have turned to one of their most powerful tools, computational simulations. These are not just simple computer models. They are vast, virtual universes built inside supercomputers that attempt to replicate the entire 14 billion-year history of the cosmos, from the initial conditions of the Big Bang to the present-day distribution of galaxies. These cosmological hydrodynamic simulations are some of the most complex and computationally expensive calculations ever performed in science. They start with a large, representative volume of the early universe, filled with dark matter and baryonic gas, and with the tiny primordial density fluctuations predicted by the theory of inflation. The simulation then evolves this virtual universe forward in time, step by step, calculating the gravitational forces between all the particles, the complex hydrodynamics of the gas as it cools, collapses, and shocks, and the subgrid physics of star formation and feedback, which are too small scale to be resolved directly, but whose effects are crucial to the overall evolution of the galaxies. The results of these simulations are nothing short of spectacular. They produce virtual universes that look remarkably and often beautifully similar to our own. They show the hierarchical formation of the cosmic web, with dark matter collapsing into filaments and halos. They show the baryonic gas falling into these halos, cooling, and forming rotating disks of stars. They show the violent mergers of galaxies, the triggering of starbursts, the growth of supermassive black holes, and the powerful feedback from supernovae and active galactic nuclei that regulates the growth of the galaxies. Projects like the Illustris and Eagle simulations have been particularly successful in this endeavor. These simulations have been able to reproduce, with remarkable accuracy, a host of observed properties of the galaxy population, such as the galaxy mass function, the morphology-density relation, and the bimodal color-magnitude diagram. These successes have given us a great deal of confidence in the overall hierarchical LCDM paradigm of galaxy formation. They have shown us that our basic picture of how the universe is put together is, in all likelihood, correct, but these simulations are not just about confirming what we already know. They are also powerful tools for discovery. By comparing the detailed predictions of the simulations with the ever more precise observations from telescopes like Hubble and Webb, we can test our understanding of the complex subgrid physics of star formation and feedback. For example, by tweaking the parameters that govern the strength of supernova feedback or AGN feedback in the simulations, we can see what effect this has on the resulting galaxy population. And we can then compare this with the real universe to see which models work best. This is a powerful, iterative process, a dialogue between theory and observation that is constantly refining our understanding of the complex, baryonic processes that shape the galaxies we see. The simulations also allow us to do something that is impossible in the real world: to run the cosmic movie in reverse. To trace the history of a simulated galaxy back in time to understand its unique formation path. We can see which mergers were important, when it had its major bursts of star formation, how its central black hole grew. This provides an invaluable tool for interpreting the snapshots of real galaxies that we see at different cosmic epochs. Despite their immense success, the current generation of cosmological simulations is not without its limitations. They still struggle to accurately model some of the more subtle aspects of galaxy formation, like the structure of the thin disks of spiral galaxies or the abundance of the smallest, faintest satellite galaxies. And they are all, ultimately, based on the assumption that the underlying LCDM model of cosmology is correct. They are powerful tools for understanding the gastrophysics of galaxy formation, but they cannot, by themselves, tell us the nature of dark matter or dark energy. The next frontier for these simulations is to incorporate new physics to explore the consequences of different models of dark matter, of modified gravity, of dynamic dark energy. And as our computational power continues to grow, we will be able to simulate larger volumes of the universe at higher resolution, capturing the complex interplay between the small-scale physics of star formation and the large-scale environment of the cosmic web with ever-increasing fidelity. The virtual universes we build inside our supercomputers are becoming an indispensable tool in our quest to understand the real one. They are a testament to the power of our physical theories and a beautiful and dynamic illustration of the grand, complex, and magnificent story of how, from the simple primordial seeds of the early universe, the rich and wonderful tapestry of galaxies we see today was born. The story of galaxy formation is a story written in gas. This is the raw material, the lifeblood of the cosmos, the fuel from which stars are born, and the medium through which the great cosmic cycles of matter and energy play out. Understanding the journey of this gas, from the diffuse primordial soup of the early universe to the dense, star-forming molecular clouds of present-day galaxies, is the key to understanding the entire history of cosmic evolution. In the beginning, the baryonic matter of the universe was a hot, ionized plasma of hydrogen and helium. After recombination, it cooled and became a neutral gas, which then began to fall into the gravitational potential wells of the dark matter halos. As this gas was pulled in, it was shocked and heated to very high temperatures, forming a hot, diffuse corona around the growing protogalaxy. For a star to form, this hot gas must be able to cool and condense. The efficiency of this cooling process is what determines the rate of star formation in a galaxy. In the early universe, the gas was metal-poor, meaning it lacked the heavy elements that are efficient coolants. This made it difficult for the first stars to form. But once the first, population 3 stars exploded as supernovae. They seeded the surrounding gas with the first heavy elements. These metals allowed the gas to cool much more efficiently, triggering a new, more vigorous, and more self-sustaining cycle of star formation. The gas in a modern star-forming galaxy like the Milky Way exists in a complex, multi-phase interstellar medium. There is a hot, ionized medium, heated by supernovae and stellar winds. There is a warm, neutral medium, and there is a cold, dense molecular medium, where the gas is in the form of molecules like molecular hydrogen and carbon monoxide. It is in the coldest, densest hearts of these giant molecular clouds that new stars are born. This interstellar medium is not a static environment. It is a dynamic, turbulent, and constantly evolving ecosystem. Gas is constantly cycling between these different phases, driven by the feedback from star formation. But the gas in a galaxy is not a closed system. Galaxies are constantly accreting fresh, pristine gas from the intergalactic medium, the tenuous gas that fills the space between galaxies. This gas is thought to be delivered to galaxies along the filaments of the cosmic web, in a process known as cold stream accretion. These cosmic rivers of cold gas can penetrate deep into the dark matter halos of galaxies, providing a direct and efficient supply of fuel for ongoing star formation in the disk. This process is thought to be particularly important for fueling the high rates of star formation seen in galaxies in the early universe. At the same time, galaxies are also losing gas. The powerful winds driven by supernovae and active galactic nuclei can be so strong that they can expel gas from the galaxy entirely, launching it into the intergalactic medium in a galactic outflow. This process is crucial for regulating the growth of galaxies and for enriching the IgM with the heavy elements forged in stars. Some of this expelled gas may cool and eventually rain back down onto the galaxy in a galactic fountain, contributing to a cosmic recycling process that can sustain star formation over billions of years. The journey of the gas is a complex and beautiful one, a journey that connects the largest scales of the cosmos with the smallest, the intergalactic with the interstellar, the process of galaxy formation with the birth of individual stars and planets, and it is a journey that we are now able to trace with unprecedented detail. Thanks to a new generation of powerful telescopes, radio telescopes can map the distribution of cold, molecular gas. Optical telescopes can map the distribution of warm, ionized gas, traced by the characteristic red glow of hydrogen alpha emission from star-forming regions. And X-ray telescopes can map the distribution of the hot coronal gas. By combining these different views, we are beginning to build a complete, multi-wavelength picture of the complex, gaseous ecosystem of galaxies, an ecosystem that is the ultimate source of all the structure, all the complexity, and all the life in the universe. The intricate interplay between dark matter and baryonic matter is at the very heart of the story of galaxy formation. Dark matter provides the gravitational scaffolding, the invisible architecture upon which the visible universe is built. But it is the baryonic matter, the gas, the stars, the dust that brings this architecture to life, that creates the light, the color, and the complexity of the galaxies we see. The relationship between these two components is a complex and dynamic one, a cosmic dance that has shaped the evolution of the universe for the past 14 billion years. The dance begins in the early universe. Dark matter, being collisionless, is able to start clumping together early on, forming the first small halos. Baryonic matter, on the other hand, is coupled to the radiation field, and its pressure prevents it from collapsing until after the universe becomes transparent at the time of recombination. After this point, the baryons are free to fall into the pre-existing dark matter halos. But the baryons are not just passive followers, they have their own rich physics. The gas can cool, it can radiate away its energy, and it can collapse to much higher densities than the dark matter. This is why the visible, baryonic part of a galaxy is typically much smaller and more concentrated than its vast, diffuse dark matter halo. The process of star formation and the subsequent feedback from supernovae and active galactic nuclei are purely baryonic processes, but they can have a profound impact on the distribution of the dark matter. The powerful outflows of gas driven by feedback can heat and expand the inner regions of a dark matter halo, potentially softening the central cusp that is predicted by simple, dark matter-only simulations. This baryonic feedback is one of the leading potential solutions to the cusp core problem, one of the small-scale challenges to the standard LCDM model. The relationship between the mass of a galaxy's stars and the mass of its dark matter halo is a crucial diagnostic for our models of galaxy formation. Observations show that this relationship is not a simple, linear one for both very low mass and very high mass halos. The efficiency of converting baryons into stars is very low. In low mass halos, supernova feedback is thought to be so efficient that it can blow most of the gas out of the shallow gravitational potential well, quenching star formation. In very high mass halos, the gas in the corona is so hot that it cannot cool efficiently, and AGN feedback is thought to prevent the gas from accreting onto the central galaxy. It is only in halos with a mass similar to that of our own Milky Way that the star formation efficiency reaches its peak. This Goldilocks effect is a beautiful example of the self-regulating nature of galaxy formation, a process that is governed by the complex feedback loop between the baryonic physics of the galaxy and the gravitational potential of its dark matter halo. But the dance between dark matter and baryons is not just about feedback. It is also about the large-scale environment. In the dense heart of a galaxy cluster, the hot X-ray emitting gas of the intracluster medium can strip the gas from a galaxy, but the dark matter, being collisionless, is unaffected. This can lead to a separation between the baryonic and dark matter components of a galaxy, a process that we can observe directly through a combination of X-ray and gravitational lensing observations. The famous bullet cluster, a system of two colliding galaxy clusters, is the poster child for this effect. The hot gas from the two clusters has collided and shocked, creating a bullet-shaped cloud of X-ray emitting gas, while the dark matter from the two clusters, which we can map through its gravitational lensing effect, has passed right through each other, seemingly unimpeded. This is some of the most direct and compelling evidence we have for the existence of collisionless dark matter. The intricate and often violent dance between the visible and the invisible, between the baryons and the dark matter, is a story that is still being unraveled. It is a story that requires a combination of large-scale cosmological simulations, high-resolution observations across the entire electromagnetic spectrum, and a deep theoretical understanding of the complex physics of the baryonic ISM. But it is a story that is at the very heart of our quest to understand how the universe we see today, with all its beauty and complexity, emerged from the simple, primordial ingredients of the early cosmos. The future of our universe, once a topic reserved for theologians and philosophers, has become a field of active and precise scientific inquiry. The discovery of dark energy and the accelerating expansion of the cosmos has provided us with a new, and in many ways, more definitive, picture of our ultimate cosmic destiny. And it is a picture that is, for the most part, a cold, dark, and lonely one. If dark energy is a true cosmological constant, an unchanging energy of the vacuum itself, as our current observations suggest, then the universe is destined for a big freeze or heat death. The accelerating expansion will continue forever. In the coming billions of years, galaxies beyond our own local group will recede from us at ever-increasing speeds, eventually crossing our cosmic event horizon and disappearing from our view forever. The night sky of the distant future will be a dark and empty place, containing only the aging stars of our own merged Milky galaxy. Over much longer timescales, on the order of trillions of years, the process of star formation will cease. As the gas reservoirs of the galaxies are exhausted, the universe will enter a degenerate era, a time when the only objects left are the cold, dead remnants of stars, white dwarfs, neutron stars, and black holes. Even these objects are not eternal. Over even more immense, almost unimaginable timescales, on the order of 10 to the power of 40 years, protons themselves are predicted to decay, causing the white dwarfs and neutron stars to slowly dissolve into a sea of radiation and leptons. The only objects left will be the black holes, and even they are not forever. Due to Hawking radiation, black holes will slowly evaporate, their mass converted into a faint, thermal radiation. The supermassive black holes at the centers of galaxies will be the last to go, taking perhaps as long as 10 to the power of 100 years to evaporate completely. After this black hole era, the universe will enter its final, eternal state, the dark era. It will be a cold, dark, and almost perfectly empty void. A universe filled with nothing but a diffuse, ever-cooling bath of photons, neutrinos, and a few stray electrons and positrons. It will be a universe in a state of maximum entropy, a state of heat death, where no further thermodynamic work is possible and nothing ever happens again. This is a bleak, but scientifically plausible vision of the ultimate fate of our cosmos. But what if dark energy is not a constant? If dark energy is a phantom energy whose density increases over time, then the future is far more violent. This leads to the Big Rip scenario. In this case, the accelerating expansion will become so powerful that it will eventually overcome all the other forces of nature. In the final moments of the universe, the repulsive force of the phantom energy will first tear apart galaxy clusters, then galaxies, then solar systems, then planets. And finally, in the last fraction of a second, it will overcome the strong nuclear force and rip apart the atoms themselves, reducing the entire cosmos to a shower of fundamental particles, each forever isolated in an infinitely expanding void. On the other hand, if dark energy is a dynamic quintessence field that could one day decay or change its sign, then the future could be very different. The acceleration could stop, and the universe could even begin to contract, leading to a big crunch, a fiery mirror image of the Big Bang. This opens up the possibility of a big bounce and a cyclic universe, an endless, self-renewing cosmos with no ultimate beginning or end. Distinguishing between these different fates is one of the primary goals of future cosmological observations. By precisely measuring the expansion history of the universe and the properties of dark energy, we can hope to determine whether our cosmos is destined for a slow, cold death, a violent, fiery rip, or an eternal cyclical rebirth. This is a quest that is not just about science. It is about our own, deepest existential questions. It is about understanding the ultimate context of our own brief and precious existence in a universe whose grand cosmic story we are only just beginning to read. The story of the universe, from its fiery birth to its potential cold demise, is a story that has been pieced together through a long and arduous process of scientific inquiry, a process that is a testament to the power and the beauty of the human mind. It is a story that has taken us from the Earth-centered cosmos of the ancients to the vast, expanding, and mysterious universe of modern cosmology. And it is a story that is far from over. We are living in a golden age of discovery, a time when a new generation of powerful telescopes and experiments is poised to answer some of the longest-standing questions in science and to open up new, unforeseen avenues of inquiry. The James Webb Space Telescope is already providing us with our deepest and sharpest views of the infant universe, revealing the first galaxies as they form from the primordial darkness. Future gravitational wave observatories, like the Laser Interferometer Space Antenna, will allow us to hear the universe, to detect the faint space-time ripples from the mergers of supermassive black holes, and perhaps even from the moment of cosmic inflation itself. New large-scale galaxy surveys will map the cosmic web with unprecedented detail, allowing us to trace the history of cosmic expansion and to probe the mysterious nature of dark matter and dark energy. And on the theoretical front, the quest for a unified theory of quantum gravity, a theory of everything, continues. A quest that promises to reveal the deepest secrets of space, time, and the very nature of reality. But for all our progress, for all our powerful theories and our magnificent instruments, we must always remember the profound wisdom of learned ignorance. The more we learn, the more we become aware of the vast, uncharted ocean of our own ignorance. The universe is not a simple puzzle to be solved, but a deep, and perhaps infinite, mystery to be explored, to be wondered at, to be lived. Every answer we find seems to lead to a new, deeper and more beautiful question. The mysteries of the quantum vacuum, of dark energy, of the origin of the arrow of time, of the nature of consciousness itself. These are not just problems for scientists. They are invitations to all of us, to a state of wonder, of curiosity, of humility. They are a reminder that the world is far stranger, far more beautiful, and far more mysterious than our everyday experience would lead us to believe. And as we stand on the shore of this great cosmic ocean, we are not just passive observers. We are the universe's own way of knowing itself. The atoms in our bodies, the consciousness in our minds, are a direct and unbroken lineage from the fiery heart of the Big Bang. We are stardust, animated by the same mysterious life force that has driven the universe's long and magnificent journey from simplicity to complexity. And the quest to understand this universe, this home, is the noblest and most meaningful adventure that we, as a species, can undertake. As you close your eyes and prepare for the quiet, restorative journey of sleep, you can feel a sense of participation in this grand, human, and cosmic story. The consciousness that is about to drift into the timeless, mysterious, and creative realm of dreams is the same consciousness that has dared to look up at the stars, to ask the biggest questions, and to begin, however tentatively, to read the silent, beautiful, and endlessly fascinating story of the cosmos. Good night, and may your dreams be as vast, as mysterious, and as wonderful as the universe itself.
The light that reaches your eye from the Andromeda Galaxy began its journey 2.5 million years ago. On Earth, at that time, our distant ancestors were just beginning to shape stone into tools, their minds not yet capable of conceiving the cosmos from which that light originated. That faint smudge of light in the night sky is a time capsule, a message from a past so deep it predates humanity itself. Every star, every distant quasar, is a similar vessel, carrying stories across gulfs of space and time that are almost impossible to comprehend. When we look up, we are not seeing the universe as it is, but as it was, a mosaic of past moments assembled by the finite speed of light. We are archaeologists of photons, piecing together a history from ancient signals that have traveled for eons. But even this vast, backward-looking vista is incomplete. There are horizons we cannot see past, boundaries defined not by distance, but by the very laws that govern reality. One such boundary is woven around an object so dense, so gravitationally dominant, that its escape velocity exceeds the speed of light itself, creating a one-way portal out of our observable universe. Black holes are not holes in the conventional sense. They are destinations. They represent the final, collapsed state of matter, a place where the familiar rules of physics are warped into an unrecognizable form. Their existence, once a purely theoretical prediction from Albert Einstein's general theory of relativity, was a mathematical ghost haunting the equations. Einstein himself was uneasy with the implication that a star could collapse so completely that it would sever itself from the rest of the cosmos, a kind of cosmic self-exile. The idea of such an object dates back even further, to the late 18th century, when the English natural philosopher John Michel and the French mathematician Pierre-Simon Laplace independently reasoned that a body sufficiently massive and compact would have an escape velocity greater than the speed of light, rendering it invisible. For over a century, this concept of a dark star remained a curiosity, a footnote in the history of science. It took Einstein's revolutionary vision of gravity as the curvature of space-time to give it a solid theoretical foundation. Yet, for decades, black holes remained phantoms of mathematics. It was not until 2019 that we captured the first direct image of this ghost's shadow, the silhouette of the supermassive black hole at the center of the galaxy M87, projected against the swirling, superheated gas of its accretion disk. This monumental achievement, produced by the Event Horizon Telescope, a global network of radio telescopes acting as a single, Earth-sized observatory, did not show us the black hole itself, but the boundary of its influence. What we saw was the edge of the abyss, the event horizon, a term that sounds both poetic and final, It is the point of no return. A spaceship could, in theory, orbit a black hole safely, just as planets orbit the sun, but the event horizon is not a physical surface you could touch. It is a demarcation in space-time. Cross it, and your future is no longer your own. Beyond this one-way membrane, the roles of space and time are inverted in a way that defies all human experience. In our familiar universe, we have freedom of movement in 3 spatial dimensions, but are relentlessly carried forward in 1 temporal dimension. We can choose to go left or right, up or down, but we cannot choose to stop moving into the future. Once you cross the event horizon, that freedom vanishes. Time becomes a spatial direction, pointing inevitably toward the center, and space becomes the dimension that flows. Moving forward in time now means moving inexorably toward the singularity, a point of supposedly infinite density and 0 volume where our understanding of physics catastrophically fails. Here, general relativity, the physics of the very large, and quantum mechanics, the physics of the very small, collide in a paradox we cannot yet resolve. This is the ultimate wall, a place where our most successful scientific theories break down, signaling not an end to reality, but an end to our ability to describe it. Some theorists, unwilling to accept an infinity at the heart of nature, propose that the singularity is not a point, but something more complex, a region where quantum gravity effects take over and prevent a total collapse. Perhaps it is a fuzzball, where the information of everything that has fallen in is encoded in a tangled mass of fundamental strings, as suggested by string theory. In this view, a black hole is not an empty void but a solid, albeit exotic, object with no true horizon or singularity. Or perhaps the singularity is a Planck star, an object compressed to the smallest possible size allowed by quantum mechanics, which then rebounds in a big bounce that could create a new universe within the black hole. This idea transforms black holes from cosmic graveyards into potential cosmic wombs, each one a seed for a new reality. Others have speculated about wormholes, theoretical tunnels through space-time that could connect distant parts of our universe or even link to parallel universes. These remain highly speculative, as creating a stable, traversable wormhole would require a form of exotic matter with negative energy, something we have never observed and are not sure can exist. More immediate, and perhaps more testable, is the question of what happens just outside the event horizon. Stephen Hawking's groundbreaking discovery in the 1970s revealed that black holes are not entirely black. Due to quantum effects near the horizon, they radiate particles, a phenomenon now known as Hawking radiation. In the quantum vacuum of empty space, pairs of virtual particles and antiparticles are constantly popping into existence and annihilating each other. Near an event horizon, it is possible for one particle of a pair to fall in while the other escapes. From a distant observer's perspective, it appears as if the black hole is emitting a faint thermal glow. This radiation is incredibly faint for large black holes, but it means they are not eternal prisons. They slowly evaporate, returning their mass and energy to the universe over timescales far longer than the current age of the cosmos. A solar mass black hole would take 10 to the power of 67 years to evaporate, while a supermassive one would take 10 to the power of 100 years, an almost unimaginable stretch of time. This slow leakage of energy raises a profound question known as the information paradox. What happens to the information of the objects that fall in? A fundamental tenet of quantum mechanics is that information can never be destroyed. It can be scrambled, like burning a book, but in principle, one could reconstruct the original information from the final state of the smoke and ash. A black hole, however, seems to erase it completely. When it evaporates, the outgoing Hawking radiation appears to be thermal and random, containing no information about what fell in. Hawking initially believed the information was lost forever, a conclusion that would have required rewriting the foundations of physics. Later, he and other physicists, such as Leonard Susskind and Gerard T. Hooft, proposed that the information might be subtly encoded in the outgoing radiation through quantum correlations, a concept related to the holographic principle, which suggests that all the information contained within a volume of space can be represented on its boundary. Another possibility The firewall hypothesis suggests a violent alternative just outside the event horizon. An impenetrable wall of high-energy particles instantly incinerates anything that tries to cross, preserving information on the outside at the cost of violating Einstein's principle of equivalence, which states that falling freely should feel no different from floating in empty space. The debate rages on, because at the heart of this question lies the key to unifying our two great pillars of physics. The gravitational influence of these objects also sculpts time itself. If you were to watch a friend fall toward a black hole from a safe distance, you would witness a strange spectacle. As they approach the event horizon, their time would appear to slow down relative to yours. Their movements would become languid, their signals redshifted to lower and lower frequencies. They would seem to hover at the edge, their image growing dimmer and redder, frozen in time for eternity from your perspective. You would never see them cross, from their perspective. However, time would pass normally. They would cross the event horizon in a finite amount of time, unaware of the moment they pass the point of no return, and continue their journey toward the singularity. This temporal distortion, known as gravitational time dilation, is not just a theoretical curiosity, it is a measurable reality. The clocks on our GPS satellites, orbiting in a slightly weaker gravitational field than we experience on the surface, run faster by about 38 microseconds per day. Without constant correction for this relativistic effect, the entire system would accumulate errors that would render it useless within hours. Black holes come in a variety of sizes, each with a different origin story. Stellar black holes, with masses a few times that of our Sun, are formed from the cataclysmic collapse of massive stars at the end of their lives. When a star more than about 20 times the mass of our Sun exhausts its nuclear fuel, the outward pressure from fusion can no longer support its immense weight, and it collapses catastrophically. The resulting supernova explosion blows the star's outer layers into space, while the core implodes to form a black hole. Intermediate mass black holes, with masses between 100 and 100,000 suns, are a more mysterious class. They are thought to form in the dense cores of globular star clusters through runaway mergers of stars, but their existence is still being actively debated and confirmed. Supermassive black holes, with masses ranging from millions to billions of times that of our Sun, reside at the centers of most large galaxies, including our own Milky Way. The one at our galactic heart, Sagittarius A star, has a mass of about 4 million suns. The origin of these behemoths is still a puzzle. Did they form from the direct collapse of immense gas clouds in the early universe? Or did they grow over billions of years by merging with other black holes and consuming vast quantities of stars and gas? Astronomers have discovered that these giants are not just passive residents of their galaxies, they are active architects. The immense energy released by material falling into a supermassive black hole can power jets of particles that travel at near light speed, blasting out of the galaxy and heating the surrounding intergalactic medium. This process, known as active galactic nucleus feedback, can regulate star formation, preventing the galaxy from growing too large too quickly. In this way, these objects, which represent the ultimate destruction of matter, are also crucial for the creation and evolution of the complex structures we see today. They are a bridge between the physics of the very large and the very small, a laboratory for testing the limits of our knowledge, and a stark reminder that the universe contains boundaries far more absolute than any we have ever encountered on Earth. Our own planet is a sanctuary of predictability and stability, but it is just one world among countless others. In recent decades, we have begun to discover that the universe is teeming with planets, a realization that has transformed our understanding of our place in the cosmos. For millennia, the stars were just points of light, their nature a mystery. The idea that they might be distant suns, with their own orbiting planets, was a philosophical speculation, not a scientific one. That changed in 1995, when astronomers Michel Mayor and Didier Queloz announced the discovery of the first exoplanet orbiting a sun-like star, 51 Pegasi b. This was not a small, rocky world like Earth, but a hot Jupiter, a gas giant orbiting its star in a scorching 4-day period, a type of planet that theory had not predicted. This discovery opened the floodgates. In the years since, Thanks to ground-based observatories and dedicated space missions like NASA's Kepler and TESS, the number of confirmed exoplanets has grown to over 5,000, with thousands more candidates awaiting confirmation. We have learned that planets are not rare, they are ubiquitous. There are likely more planets than stars in our galaxy, meaning there are hundreds of billions of them in the Milky Way alone. The methods used to detect these distant worlds are triumphs of ingenuity. The most prolific method is the transit technique, used by Kepler and TESS. It involves staring at a patch of sky and monitoring the brightness of tens of thousands of stars simultaneously. If a planet passes in front of its star from our point of view, it will block a tiny fraction of the starlight, causing a slight periodic dip in the star's brightness. The size of the dip reveals the planet's size, and the time between dips reveals its orbital period. It is like detecting a gnat flying in front of a searchlight from miles away. The radial velocity method, which discovered 51 Pegasi b, looks for the gravitational tug of a planet on its star. As planet orbits, it causes its star to wobble slightly. This wobble can be detected as a tiny, periodic shift in the star's light, a Doppler effect, similar to the change in pitch of a siren as an ambulance passes by. This method can tell us the planet's mass. By combining these two methods, astronomers can determine a planet's density, giving us our first clues about its composition, whether it is a rocky world, a gas giant, or something in between. The diversity of these newly discovered worlds has shattered our expectations. We have found planets orbiting two stars, so-called circumbinary planets, where one could witness a double sunset reminiscent of the fictional planet Tatooine. We have found super-Earths, rocky planets larger than our own, and mini-Neptunes, gaseous worlds smaller than our ice giants. Two classes of planets that are common in the galaxy but absent from our own solar system. There are planets so close to their stars that their surfaces are molten oceans of lava, and eyeball planets, tidally locked worlds with one side permanently facing their star in perpetual daylight and the other in perpetual frozen night. We have even found rogue planets, worlds that do not orbit any star but wander through the cold, dark expanse of interstellar space, having been ejected from their home systems long ago. The ultimate goal of this search, however, is to find another Earth, a planet that could potentially harbor life. The search focuses on the habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. One of the most promising systems discovered so far is TRAPPIST-1, located about 40 light-years away. It is a tiny, cool red dwarf star orbited by 7 Earth-sized rocky planets. At least 3 of them are located within the habitable zone, raising the tantalizing possibility of worlds with oceans, clouds, and perhaps life. The James Webb Space Telescope is now capable of studying the atmospheres of some of these nearby exoplanets. By analyzing the starlight that passes through a planet's atmosphere during a transit, we can look for the chemical fingerprints of different molecules. We can search for biosignatures, gases like oxygen, methane, and water vapor, which on Earth are produced in large quantities by living organisms. The detection of such a combination of gases in the atmosphere of a distant world would not be definitive proof of life, but it would be the most profound discovery in human history, a sign that we are not alone in this vast, silent universe. It would force us to redraw the boundaries of biology and confront the possibility that the story of life is a cosmic one, not just a terrestrial one. Our instruments, extensions of our senses, peer out into the cosmos and reveal a universe of breathtaking complexity. Yet, for every galaxy we catalog and every star we analyze, we are confronted with the humbling reality that what we see is not the full picture. It is merely a sliver, a luminous foam on the surface of a vast, dark ocean. The very motion of the stars and galaxies tells a story of an invisible presence, a gravitational influence that cannot be accounted for by the matter we can detect. This unseen component, dubbed dark matter, makes up approximately 27% of the universe's mass energy content, outweighing all the ordinary matter of stars, gas, and dust by a factor of more than 5 to 1. It is the silent, invisible giant that holds the cosmos together, the unseen puppeteer pulling the strings of galactic motion. Its existence represents a profound boundary in our perception, a realm of reality that lies beyond the reach of our eyes and telescopes, detectable only through its gravitational shadow. The first whispers of its existence came in the 1930s from the Swiss-American astronomer Fritz Zwicky, a brilliant and famously irascible character. While observing the Coma Cluster, a dense swarm of over 1,000 galaxies, Zwicky noticed something deeply puzzling. He measured the velocities of the individual galaxies and found them to be moving far too quickly. According to the laws of gravity as understood at the time, the visible matter in the cluster, the combined mass of all its stars, was not nearly enough to keep these galaxies gravitationally bound. The cluster should have been flying apart. To solve this puzzle, Zwicky postulated the existence of Dunkel Materiae, or dark matter, an unseen mass providing the extra gravitational glue. His idea was largely ignored for decades, considered too radical a solution for an observational anomaly that might have other explanations. The scientific community was not yet ready to accept that the universe was mostly invisible. The evidence, however, continued to mount, becoming undeniable in the 1970s with the pioneering work of astronomers Vera Rubin and Kent Ford. They meticulously studied the rotation of spiral galaxies, including our own neighbor, Andromeda. They expected to find that stars at the outer edges of a galaxy would orbit more slowly than those closer to the center, just as the outer planets in our solar system move more slowly than the inner ones. Following Kepler's laws, this is because most of the visible mass of a galaxy is concentrated in its central bulge. Instead, they found something completely unexpected. The star's orbital speeds remain surprisingly constant, or even increased, far out from the galactic center. This flat rotation curve was inexplicable unless the galaxy was embedded in a vast, spherical halo of invisible matter, extending far beyond the visible disk of stars. This halo contained the bulk of the galaxy's mass, a silent, gravitational cocoon that governed the motion of the stars within it. Rubin's work provided the smoking gun, transforming dark matter from a fringe idea into a central problem of modern cosmology. Further evidence comes from the phenomenon of gravitational lensing, another prediction of Einstein's general relativity. Massive objects warp the fabric of space-time, causing light from more distant objects to bend around them, much like a lens focuses light. By observing how the light from distant galaxies is distorted as it passes through galaxy clusters, astronomers can map the distribution of mass in those clusters. These maps consistently show that the mass is concentrated not where the visible galaxies are, but in a much larger, smoother distribution of invisible matter. We can see the effect of dark matter's gravity, even if we cannot see the matter itself. It is like inferring the presence of an invisible person by the footprints they leave in the snow. A striking example of this is the Bullet Cluster, which is actually two galaxy clusters that have passed through each other. The hot gas of the clusters, which contains most of the ordinary matter, collided and slowed down, while the dark matter, which does not interact except through gravity, passed straight through. The result is a clear separation of the visible matter from the gravitational mass, a direct observation of dark matter's ghostly nature. The cosmic microwave background, the afterglow of the Big Bang, also carries the imprint of dark matter. This ancient light, released just 380,000 years after the universe began, is remarkably uniform, but it contains tiny temperature fluctuations. These fluctuations represent the seeds of all future structure, the slight density variations that would eventually grow into the vast galaxies and clusters we see today. However, the fluctuations are too small to have grown into these structures in the 13.8 billion years since the universe began. If only ordinary matter existed, the radiation pressure in the early universe would have prevented ordinary matter from clumping together effectively. Dark matter, being immune to this pressure, could begin to collapse under its own gravity much earlier, forming deep gravitational wells into which ordinary matter could later fall, accelerating the process of structure formation. Without dark matter, the universe today would be a much smoother, more uniform place, devoid of the complex cosmic web that we observe. But what is this mysterious substance? The most straightforward answer, that it is simply ordinary matter that does not shine things like brown dwarfs, cold gas clouds, or rogue planets, collectively known as machos, has been largely ruled out by observational constraints from gravitational microlensing surveys and Big Bang nucleosynthesis, which places tight limits on the total amount of ordinary or baryonic matter in the universe. The leading candidates are therefore hypothetical subatomic particles that were forged in the heat of the Big Bang and have survived to the present day. These particles would not interact with light or any other form of electromagnetic radiation, which is why they are dark. They would interact only through gravity and possibly the weak nuclear force. The most popular class of candidates is known as WIMPs, or weakly interacting massive particles. These particles would be heavy, perhaps 100 times the mass of a proton, and would be moving relatively slowly, which is why this model is often called cold dark matter. Another promising candidate is the axion, a much lighter, hypothetical particle proposed to solve a problem in the theory of the strong nuclear force called the strong CP problem. If they exist, axions would have been produced in enormous quantities in the early universe, and would form a vast, cold sea of particles, behaving more like a coherent wave than individual particles. Scientists are engaged in a three-pronged search for these elusive particles, a global effort to shine a light on the dark universe. Direct detection experiments are located deep underground, in mines or tunnels like the Sanford Underground Research Facility in South Dakota, or the Gran Sasso National Laboratory in Italy, to shield them from the constant rain of cosmic rays and other background radiation. These experiments use large, ultra-pure detectors made of materials like liquid xenon or germanium crystals, waiting for the vanishingly rare event of a dark matter particle bumping into an atomic nucleus and leaving a tiny, detectable flash of light or heat. So far, despite decades of searching and increasingly sensitive experiments, no definitive signal has been found, leading to what some have called a WIMP-pocalypse, though the search continues to probe for lighter or more weakly interacting particles. Indirect detection experiments search for the products of dark matter annihilation. If two dark matter particles were to collide, they could annihilate each other, producing a shower of more familiar particles, such as gamma rays, neutrinos, or antimatter particles like positrons, which our telescopes could detect. Telescopes like the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer on the International Space Station are scanning the sky for an excess of these signals coming from regions where dark matter is expected to be dense, like the center of our galaxy or nearby dwarf galaxies. Some tantalizing hints have been found, but none have yet risen to the level of a conclusive discovery. Finally, particle colliders like the Large Hadron Collider at CERN are trying to create dark matter particles directly. By smashing protons together at enormous energies, physicists hope to recreate the conditions of the early universe and produce new, undiscovered particles. If a new particle is created that escapes the detector without leaving a trace, it could be a sign of a WIMP or a similar particle being produced and flying away, its presence inferred only by the missing energy and momentum in the collision debris. While the evidence for dark matter is compelling, a minority of physicists advocate for an alternative explanation that our understanding of gravity is incomplete. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in the 1980s, suggests that Newton's law of gravity changes at very low accelerations, such as those experienced by stars in the outer parts of galaxies. This modification would explain the flat rotation curves without the need for dark matter. While MOND has had some remarkable success in explaining the dynamics of individual galaxies using only their visible matter, it has struggled to explain the observations of galaxy clusters and the cosmic microwave background without becoming more complex and less elegant than the standard dark matter model. For now, the dark matter hypothesis remains the dominant paradigm, a placeholder for a profound gap in our knowledge. It is the invisible architecture of the cosmos, the scaffolding upon which the visible universe is built. The quest to identify its nature is one of the most urgent tasks in modern physics, for its discovery would not only solve a cosmological mystery, but could also reveal a whole new sector of particles and forces, a dark realm that mirrors our own, connected only by the gentle, persistent pull of gravity. But dark matter is not the only invisible component dominating the cosmic inventory. An even more mysterious substance is pushing the universe apart, shaping its ultimate destiny. The cosmic stage is not static. Since the moment of its birth, the universe has been expanding, a discovery made by Edwin Hubble in the 1920s that reshaped our understanding of our place in cosmic history. For most of the 20th century, the prevailing question was whether this expansion would continue forever or if the mutual gravitational attraction of all the matter in the universe would eventually slow it down, halt it, and perhaps even reverse it into a cosmic collapse, a big crunch. The fate of the universe seemed to hang in the balance, a cosmic battle between the outward momentum of the Big Bang and the inward pull of gravity. The answer, when it came, was one of the most surprising in the history of science. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were studying distant type Ia supernovae, a type of stellar explosion that serves as a reliable standard candle for measuring cosmic distances to precisely measure the rate at which the expansion was slowing down. But they found the opposite. The distant supernovae were dimmer and therefore farther away than they should have been. The expansion of the universe is not slowing down, it is accelerating. This was a revelation that turned cosmology on its head, earning its discoverers the Nobel Prize in Physics in 2011. To explain this accelerated expansion, there must be some form of energy inherent in the fabric of space itself, a repulsive force that is pushing the universe apart, acting in opposition to gravity. This mysterious component was named dark energy, and according to our best current measurements, it constitutes about 68% of the total energy density of the universe. It is the dominant force in the cosmos today, yet its nature remains one of the deepest mysteries in all of science. It is not matter, it is not radiation. It seems to be a property of the vacuum, an intrinsic energy of empty space. Its existence defines a new kind of cosmic boundary, a horizon beyond which information can never reach us, created by the accelerating expansion of space-time itself. One of the leading explanations for dark energy is the cosmological constant, an idea that Albert Einstein originally introduced into his equations of general relativity in 1917. He added it to counteract the pull of gravity and achieve a static, unchanging universe, which was the prevailing belief at the time. When Hubble discovered the expansion of the universe, Einstein famously discarded the cosmological constant, calling it his biggest blunder. The irony is that his blunder may have turned out to be his most prophetic insight. If dark energy is indeed the cosmological constant, represented by the Greek letter lambda, it means that every cubic centimeter of empty space contains a small, fixed amount of this repulsive energy. As the universe expands, more space is created, and with it, more dark energy, which in turn drives the expansion to accelerate even faster. This creates a feedback loop, a runaway expansion that will shape the ultimate destiny of the cosmos. The consequences of this accelerating expansion are profound and somewhat melancholic. In the distant future, perhaps 100 billion years from now, all galaxies outside our own local group, the small cluster of galaxies that includes the Milky Way and Andromeda, will have been pushed so far away by the expansion of space that their light will no longer be able to reach us. The space between us and them will be stretching faster than the speed of light. For a future observer in our galaxy, the night sky will be a dark and lonely place. The rich tapestry of distant galaxies will have vanished beyond a cosmic horizon, leaving only the stars of the Milky Way and its immediate neighbors, which will have by then merged into a single, large elliptical galaxy. Future astronomers would have no way of knowing that other galaxies exist, or that the universe began with a Big Bang. The evidence for these fundamental truths would be lost forever, carried away by the relentless expansion of space. It is a sobering thought that our current moment in cosmic history may be a uniquely privileged one, a time when the universe is old enough to have formed complex structures, but young enough that the evidence of its origins is still visible. Alternative theories for dark energy exist, though they are less favored. One is the idea of quintessence, a dynamic field that fills space, similar to the cosmological constant, but with an energy density that can change over time. Depending on how this field evolves, the acceleration of the universe could slow down, stop, or even become more extreme in the future. Another possibility is that general relativity itself needs to be modified on the largest cosmic scales. Just as Mondi proposes to modify gravity on galactic scales, perhaps the observed acceleration is not due to a new form of energy, but is a manifestation of a more complex gravitational theory than Einstein's. The most tantalizing connection, however, is with the quantum world. Quantum field theory predicts that the vacuum should be teeming with virtual particles, creating a vacuum energy that has properties very similar to the cosmological constant. The problem is that when physicists try to calculate the expected amount of this vacuum energy, the result is catastrophically wrong. The theoretical prediction is about 10 to the power of 120 times larger than the observed value of dark energy. This discrepancy, known as the cosmological constant problem, has been called the worst theoretical prediction in the history of physics. It suggests a profound misunderstanding in our connection between the quantum world and the cosmos at large. Dark matter and dark energy together constitute 95% of the universe. All of our physics, all of our experience is based on the remaining 5% of ordinary matter. We are like explorers who have landed on a new continent and, having studied a single beach, believe we understand the entire landmass. The rest lies hidden, its nature and properties a mystery. Dark matter acts as the universe's sculptor, its gravitational pull gathering matter into the cosmic web of galaxies and clusters. Dark energy acts as the universe's accelerator, its repulsive force driving everything apart. It is a grand cosmic struggle, a tug of war between attraction and repulsion that will determine the ultimate fate of the universe. If dark energy is the cosmological constant and remains constant, the universe is heading toward a big freeze or heat death. It will continue to expand and cool indefinitely. Stars will burn out, black holes will evaporate, and the cosmos will become a cold, dark, and empty place. A diffuse soup of elementary particles at a temperature infinitesimally close to absolute zero. If dark energy's strength increases over time, a more violent end known as the Big Rip could occur. The accelerating expansion would become so powerful that it would eventually overcome not just the gravity holding galaxies and stars together, but the electromagnetic and nuclear forces holding atoms and even atomic nuclei together. The entire fabric of reality would be torn apart. The quest to understand these dark components is therefore not just an academic exercise. It is a quest to understand the fundamental nature of our reality and its ultimate destiny. It is a journey into an invisible landscape that shapes everything we see, a reminder that the universe is far stranger and more mysterious than we could ever have imagined from our small, brightly lit corner of it. The familiar flow of time, a river carrying us from a fixed past to an open future, is a deeply ingrained human intuition. It seems to govern our lives with an absolute, unyielding consistency, a universal clock ticking away the moments of existence. Yet, at the dawn of the 20th century, Albert Einstein dismantled this intuition with his special and general theories of relativity. He showed that time is not an absolute metronome ticking at the same rate for everyone in the universe. Instead, it is a malleable, relative quantity, woven together with space into a single, dynamic fabric called space-time. Time can be stretched and compressed, its passage dependent on an observer's motion and the strength of the gravitational field they inhabit. This shattering of the absolute nature of time represents a crossing of a profound conceptual boundary, from the classical world of Newton to the strange, relativistic cosmos we now know we inhabit. The phenomenon of time dilation, a core prediction of special relativity, states that for a moving observer, time passes more slowly than for a stationary one. The faster you move through space, the slower you move through time. If one of a pair of identical twins were to embark on a journey through space at a velocity approaching the speed of light, say 99.9% of it, upon their return to Earth after what felt like 5 years to them, they would find that over a century had passed for their stay-at-home sibling. The traveling twin would be biologically younger. This is not science fiction, it is a confirmed physical reality, demonstrated countless times with atomic clocks on airplanes, rockets, and satellites. It is the reason that time travel to the future is, in principle, physically possible. Gravity, according to general relativity, also warps time. The stronger the gravitational field, the slower time flows. A clock at sea level will tick slightly more slowly than a clock on a mountaintop, where the Earth's gravity is marginally weaker. This effect becomes extreme near massive objects. If you could hover near the surface of a neutron star, a city-sized remnant of a collapsed star with a mass greater than our sun, for every hour that passed for you, years or even decades could pass for a distant observer. At the event horizon of a black hole, this effect reaches its limit. From the perspective of the outside universe, time for an object at the horizon effectively stops. This malleability of time opens up the theoretical possibility of one-way travel into the future. By traveling at relativistic speeds or spending time in a strong gravitational field, one could jump forward in time relative to the rest of the universe. Travel to the past, however, is a far more problematic concept, fraught with paradoxes and theoretical hurdles. While Einstein's equations do not explicitly forbid it, they suggest that it would require exotic physical constructs that may be impossible to create. One such construct is a wormhole, or an Einstein-Rosen bridge, which could theoretically act as a shortcut between two different points in space-time. If the two mouths of a wormhole were manipulated in a specific way, one kept stationary and the other taken on a high-speed journey, it could become a time machine, allowing travel between the two different moments in time to which the mouths are connected. Another theoretical possibility involves infinitely long, rotating cylinders, known as Tipler cylinders, which could drag space-time around them so violently that they create closed time-like curves, pathways that loop back on themselves in time. However, both of these scenarios would likely require vast amounts of negative energy to stabilize, and many physicists believe that the laws of nature may conspire to prevent their formation. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics themselves, perhaps through yet unknown quantum gravity effects, prevent the creation of time machines on a macroscopic scale. This would protect the universe from the logical contradictions that could arise from backwards time travel, such as the famous grandfather paradox, where a traveler goes back in time and prevents their own grandfather from meeting their grandmother, thus preventing their own birth and their ability to travel back in time in the first place. From a quantum perspective, time becomes even stranger, and the boundary between past, present, and future begins to blur. The world of quantum mechanics is one of probabilities and uncertainties, where particles can exist in multiple states at once, in a state of superposition, until they are measured. In some experiments, like the delayed choice quantum eraser, it appears as if a choice made in the present can retroactively influence an event that has already happened in the past. This does not mean we can send information back in time, but it does suggest that the relationship between cause and effect at the quantum level is not as straightforward as it is in our classical world. The phenomenon of quantum entanglement, which Einstein called spooky action at a distance, further complicates our notion of time and space. When two particles are entangled, their fates are linked, no matter how far apart they are. If you measure a property of one particle, you instantly know the corresponding property of the other. Faster than light could travel between them. This seems to violate the principle of locality, but it does not allow for faster than light communication. It simply reveals a deep, non-local connection that is a fundamental feature of reality. These quantum mysteries have led some physicists to speculate about the very nature of time itself. John Wheeler's participatory anthropic principle suggests that the universe, in a sense, comes into being through the act of observation. In this view, observers are not passive witnesses but active participants in the creation of reality, and the past of the universe may not be fully fixed until it is observed. Other interpretations, like the many worlds interpretation, suggest that every quantum measurement causes the universe to split into multiple branches, with each possible outcome realized in a separate, parallel universe. In this framework, all possible histories are real, and the arrow of time as we perceive it is just the path we happen to be following through one branch of this vast, ever-splitting tree of realities. There are even more radical ideas that propose time may not be a fundamental aspect of reality at all. In some approaches to quantum gravity, such as loop quantum gravity, space-time is not a smooth, continuous fabric, but is made of discrete, indivisible units, or quanta of space and time. At the Planck scale, At this most fundamental level, the concept of a smooth flow of time may dissolve. Instead, time might be an emergent phenomenon, a statistical effect that arises from the more fundamental interactions of these quantum units. Much like temperature is not a property of a single molecule, but an emergent property of the average motion of many molecules. In this view, our perception of a flowing river of time would be an illusion, a macroscopic approximation of a more complex, timeless quantum reality. The universe would be a static block of space-time, where the past, present, and future all exist simultaneously, and our consciousness simply moves through this block, creating the illusion of passage. This idea, known as eternalism, has profound philosophical implications. Suggesting that all moments are equally real, this brings us to the very concept of nothingness. Our intuition tells us that empty space is a void, a state of absolute nothing. But quantum field theory reveals that what we call the vacuum is far from empty. It is a seething cauldron of activity, a quantum foam where virtual particles and antiparticles constantly pop into and out of existence, borrowing energy from the vacuum for fleeting moments, as allowed by Heisenberg's uncertainty principle. This zero-point energy of the vacuum is real and has measurable effects, such as the Casimir effect, where two uncharged metal plates placed very close together in a vacuum are pushed together by the pressure of the virtual particles outside them, being greater than the pressure between them. This invisible's energetic sea is the true ground state of reality, the baseline upon which all matter and energy exist. It may even be the source of everything. Some cosmological models, like those proposed by Lawrence Krauss and Alexander Vilenkin, suggest that our entire universe could have arisen as a quantum fluctuation in this pre-existing vacuum. A universe from nothing, though this nothing is a far cry from the philosophical concept of absolute non-existence. It is a nothingness filled with potential. The quantum vacuum is the ultimate boundary, the interface between existence and non-existence, and it may hold the key to understanding the origin of the universe. The constant roiling fluctuations in the vacuum in the universe's first moments are thought to have been stretched to cosmological scales by the process of inflation, becoming the seeds for the large-scale structure of galaxies and clusters we see today. The faint temperature variations in the cosmic microwave background are a direct snapshot of these quantum jitters, writ large across the sky. So, the largest structures in the universe may have their origins in the smallest, most ephemeral quantum fluctuations in the void, whether time is a fundamental river, a branching tree, a static block, or an emergent illusion. Its true nature remains one of the deepest and most personal mysteries of the cosmos. It is the canvas on which our lives are painted, yet its secrets are woven into the very fabric of reality. From the quantum foam at the smallest scales to the expanding horizons of the universe at the largest. Understanding time is not just a challenge for physics. It is a journey into the heart of what it means to exist, and it forces us to confront the possibility that our entire reality is just one of many, a single story in an infinite cosmic library. The notion that our universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, might not be the only one, is an idea that has migrated from the realm of science fiction and philosophy into the frontiers of theoretical physics. The concept of the multiverse is not a single, coherent theory, but a collection of different models, each arising from a different area of physics, and each proposing a different kind of parallel reality. It pushes the boundary of our cosmic context to its ultimate limit, suggesting that our entire universe is but a single component in a far grander, and perhaps infinite, structure. The implications of this are staggering, forcing us to reevaluate not only our place in the cosmos, but the very uniqueness of our existence and the physical laws that govern it. One of the most compelling arguments for a multiverse comes from the theory of cosmic inflation. Inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential, superluminal expansion, driven by a quantum field called the inflation field. It stretched from a size smaller than an atom to a size larger than a galaxy in an instant. This theory elegantly explains several key features of our universe, such as its large-scale uniformity and its flat geometry. In many models of inflation, developed by physicists like Andrei Linde and Alan Guth, this process, once started, is eternal. While inflation may have ended in our pocket of space-time, creating our observable universe, it continues in other regions, constantly spawning new bubble universes, each with its own Big Bang, like bubbles forming in a pot of boiling water. New universes would constantly nucleate out of the eternally inflating background. These other bubble universes could be vastly different from our own. The properties of each universe would depend on how the inflaton field settled down into its low-energy state. This could lead to universes with different physical constants, different numbers of spatial dimensions, and even different fundamental particles and forces. Most of these universes would likely be sterile and uninhabitable, perhaps collapsing back on themselves moments after they form, or expanding so rapidly that no structures could ever coalesce. Our universe, with its seemingly fine-tuned laws, would be one of the rare, successful bubbles where conditions were right for complexity and life to emerge. This Level 2 multiverse provides a naturalistic explanation for the fine-tuning problem, but it comes at the cost of postulating an infinite number of unobservable other worlds. A second type of multiverse arises from the strange rules of quantum mechanics. The many-worlds interpretation, proposed by Hugh Everett in the 1950s as his PhD thesis, offers a radical solution to the measurement problem in quantum physics. In the standard Copenhagen interpretation, a quantum system exists in a superposition of all possible states until it is measured, at which point its wave function collapses into a single, definite state. Everett found this collapse to be an arbitrary and unnecessary addition to the underlying mathematics of quantum theory. He suggested that the collapse never happens. Instead, all possible outcomes of a quantum event actually occur, each in its own separate universe. Every time a quantum choice is made, whether a radioactive atom decays or not, whether a particle passes through the left slit or the right reality splits. In this Level 3 multiverse, there is an incomprehensibly vast, constantly branching tree of parallel realities. In one universe, you are reading this sentence. In another, you looked away a moment ago. In one, the dinosaurs were never wiped out by an asteroid. In another, humanity has already colonized the stars. All of these universes would be equally real, existing simultaneously in a different part of a vast, abstract mathematical space known as Hilbert space. We would have no way of interacting with them, as they are decoherent from our own world. The many worlds interpretation is elegant in its mathematical simplicity, as it requires no extra ad hoc postulates like wave function collapse. But it is ontologically extravagant, requiring the existence of a near infinite number of parallel versions of ourselves and our world. A third possibility for a multiverse comes from string theory, the leading candidate for a unified theory of everything that reconciles general relativity and quantum mechanics. String theory posits that the fundamental constituents of reality are not point-like particles but tiny, one-dimensional vibrating strings. For the theory to be mathematically consistent, it requires the existence of extra spatial dimensions beyond the 3 we experience, typically 6 or 7 of them. These extra dimensions are thought to be curled up or compactified on a scale too small for us to detect. The geometry of these extra dimensions, the shape of the so-called Calabi-Yau manifolds, determines the vibrational modes of the strings, which in turn determine the properties of the particles and forces in our universe. The problem is that string theory does not predict a unique way for these extra dimensions to be curled up. Instead, it allows for a vast number of possible solutions, perhaps as many as 10 to the power of 500. Each of these solutions corresponds to a different vacuum state, a different set of physical laws and constants. This collection of all possible universes is known as the string theory landscape. Our universe would be just one of these many possible worlds. In a related concept from M-theory, an extension of string theory, our universe could be a 3-dimensional brain floating in a higher dimensional space, or bulk. There could be other brains, other universes, floating parallel to our own in this higher dimensional reality. These brain worlds could be just millimeters away from us in the extra dimensions, but we would be unable to perceive them because our matter and light are confined to our own brain. Gravity, however, might be able to leak between the brains, which could explain why gravity is so much weaker than the other fundamental forces. In some models, the Big Bang itself could have been caused by the collision of two such brains. A fourth, and perhaps the most straightforward, type of multiverse is simply a consequence of an infinite universe. Our observable universe is the region of space from which light has had time to reach us since the Big Bang, a sphere about 93 billion light-years in diameter. But there is no reason to believe that the universe ends at this horizon. If space is spatially infinite, as current observations suggest, and the distribution of matter and energy is roughly uniform on the largest scales, then in that infinite space, every possible configuration of particles within a finite volume must eventually repeat far beyond our observable horizon. There would be other regions of space identical to our own. In this level 1, or quilted multiverse, there would be an infinite number of regions the size of our observable universe. And in some of them, the arrangement of matter would be exactly the same as it is here. Somewhere out there, there would be another Earth, with another version of you, living a life identical to yours. And there would be other regions where things are almost identical, but with one tiny difference. This is not a different set of physical laws, but simply a consequence of infinite space and finite possibilities. The existence of a multiverse, in any of these forms, could offer a neat explanation for the apparent fine-tuning of our universe. The fundamental constants of nature, the strength of gravity, the mass of the electron, the value of the cosmological constant seem to be precisely dialed in to the narrow range that allows for the formation of complex structures like stars, planets, and life. If these values were even slightly different, the universe would be a sterile, empty place. This fine-tuning has led some to argue for a divine creator. The multiverse provides a naturalistic alternative if there are an infinite number of universes, each with a random set of physical constants. Then it is no surprise that we find ourselves in one of the rare universes where the conditions are right for our existence. We are here because we could not be anywhere else. This is the anthropic principle in its strongest form. While the concept of a multiverse is tantalizing, it remains on the very edge of science, blurring the line with metaphysics. By definition, these other universes are likely to be forever beyond our ability to directly observe. This has led to a fierce debate about whether the multiverse is a scientific theory at all, as a theory should be falsifiable. Proponents argue that it is a natural consequence of our best current theories, like inflation and string theory, and that we should follow the mathematics where it leads. They also point to potential, indirect ways to test these ideas. The collision of our bubble universe with another in the distant past could have left a detectable signature, a bruise in the cosmic microwave background. The detection of extra dimensions or specific particles predicted by string theory at the Large Hadron Collider could lend support to the brain world scenario. For now, the multiverse remains a deeply compelling but unproven idea, a grand and humbling vision of a reality far vaster than our ancestors, or even the scientists of a century ago, could ever have dreamed. It suggests that our entire cosmos, in all its unimaginable scale and complexity, may be just a single grain of sand on an infinite cosmic shore, one story among an infinity of others, all playing out across the boundless landscape of reality. At the end of our cosmic journey, after crossing the boundaries of observation, perception, and reality itself, we are left to confront the final frontiers, the boundary of the future, and the boundary of meaning. Having contemplated the possibility of infinite worlds, we return to our own, to the singular story of our universe, and ask the ultimate questions. What is its final chapter, and what is our role in its unfolding narrative? The story of the universe is one of constant transformation, from the fiery birth of the Big Bang to the intricate dance of galaxies we see today. But all stories have an end, and the laws of physics, particularly the second law of thermodynamics, suggest that our universe is no exception. The second law of thermodynamics states that in a closed system, entropy, a measure of disorder or randomness, always increases. The universe, as a whole, appears to be a closed system, and so it is relentlessly marching toward a state of maximum entropy, a final, uniform equilibrium. The discovery of dark energy and the accelerating expansion of the universe has given us a clearer, though more desolate, picture of what this end might look like. If dark energy is a cosmological constant, the prevailing scenario for the universe's ultimate fate is the Big Freeze, or heat death. The timeline for this future is mind-bogglingly vast. In about 4.5 billion years, our Milky Way galaxy will collide and merge with the Andromeda galaxy, forming a new, larger elliptical galaxy, which some have dubbed Milkomeda. This will be a spectacular, but not particularly destructive, event for individual stars. In about 100 billion years, the accelerating expansion will have carried all other galaxies beyond our cosmic horizon, leaving Milkomeda as a solitary island in an endless, empty void. Over the next trillions of years, the process of star formation will cease as the last reserves of interstellar gas are exhausted. The existing stars will one by one burn out. The longest-lived stars, the small, cool red dwarfs, will continue to shine for up to 100 trillion years, but they too will eventually flicker out, becoming cold, dark black dwarfs. The universe will enter its degenerate era, populated only by the dead remnants of stars, black dwarfs, neutron stars, and black holes. Even these remnants are not eternal. Over timescales so long they defy description, 10 to the power of 40 years or more, protons themselves may decay, causing the dead stars and planets to dissolve into a bath of radiation and lighter particles. The only remaining objects of significance will be black holes, but they too will succumb to entropy. Through Hawking radiation, they will slowly evaporate, their mass converted back into energy. The process will be agonizingly slow, but inevitable. The last supermassive black holes will finally disappear after perhaps 10 to the power of 100 years, leaving behind a universe that is a cold, dark, and unimaginably dilute soup of photons, neutrinos, and other elementary particles, all at a temperature infinitesimally close to absolute zero. This is the ultimate state of equilibrium, the heat death of the universe, a future of eternal, unchanging darkness. But what if dark energy is not constant? If its repulsive force were to grow stronger over time, a more violent end, the Big Rip, could await us. In this scenario, the accelerating expansion would become so powerful that in the final moments of the universe, it would overcome all other forces. First, it would tear apart clusters of galaxies, then the galaxies themselves. In the final minutes, it would overcome the gravity holding stars and planets together. In the final fractions of a second, it would overwhelm the electromagnetic force, ripping atoms apart. Finally, it would tear apart atomic nuclei themselves, reducing the entire universe to a sea of unbound elementary particles. A less likely, but still possible, scenario is the Big Crunch. If dark energy were to reverse its character and become attractive, the expansion of the universe could slow, halt, and reverse. The universe would begin to contract, heading toward a fiery end as everything collapses back into a singularity, a mirror image of the Big Bang. Some theories, like loop quantum gravity, suggest that this crunch could lead to a big bounce, giving birth to a new, expanding universe in an eternal cycle of creation and destruction. In the face of these immense, impersonal cosmic fates, it is natural to ask about the fate of life and intelligence. If we are the only intelligent species in our galaxy, or even our observable universe, a question arises why. This is the heart of the Fermi paradox. The universe is ancient and vast. There has been ample time for other technological civilizations to arise and spread throughout the galaxy. Yet, we see no evidence of them, no megastructures, no interstellar communications, no signs of cosmic engineering. Where is everybody? One possible answer is the Great Filter, the idea that there is some evolutionary or technological hurdle that is extremely difficult for life to overcome. This filter could be in our past, meaning that the emergence of life, or complex life, or intelligence, is an incredibly rare event, making us one of the first, or only, civilizations to exist. Or, more ominously, the Great Filter could be in our future. Perhaps all advanced civilizations inevitably destroy themselves through nuclear war, environmental collapse, or the creation of uncontrollable artificial intelligence. Or perhaps there is some natural cosmic threat that inevitably wipes them out. In this case, the silence of the cosmos would be a warning. Other solutions to the paradox are less dramatic. Perhaps interstellar travel is simply too difficult and expensive for any civilization to pursue on a large scale. Perhaps they are out there, but they are deliberately hiding from us, observing us as if we are in a cosmic zoo or nature preserve, a hypothesis known as the zoo hypothesis. Or perhaps their biology and technology are so different from our own that we would not even recognize their signals or their presence. They could be living in the interiors of stars, or as vast, distributed intelligences in the cold of interstellar space. The silence of the universe remains one of the most profound and unsettling mysteries, a mirror reflecting our own hopes and fears for the future of humanity. This brings us back to ourselves, to this brief, flickering moment of consciousness on a small, rocky planet, faced with the vastness of cosmic time and the apparent indifference of the universe. What is our place for millennia? We believed we were the center of creation. Science has shown us that we are not the physical center of anything. We live on an unremarkable planet, orbiting an average star, in a typical galaxy, in a possibly infinite sea of other universes. This can be seen as a cosmic demotion, a story of our ever-dwindling significance. But there is another perspective. We are, as far as we know, the only beings in the universe capable of understanding its laws, appreciating its patterns, and asking these questions. We are made of stardust, the ashes of long-dead stars, the carbon in our cells, the oxygen we breathe, the iron in our blood, all were forged in the hearts of stellar furnaces and scattered across the galaxy by supernova explosions. We are not separate from the cosmos, we are a part of it. We are the universe made conscious. In the words of Carl Sagan, we are a way for the cosmos to know itself. This idea bestows upon us a unique and profound responsibility. In a universe that may be largely devoid of meaning, it is our consciousness that creates it. We are the storytellers, the artists, the lovers, the scientists. We are the ones who look up at the silent, starry sky and see not just points of light, but the history of the universe and the potential for the future. We are the ones who care. The physicist Richard Feynman once compared science to being a child in a vast library, where all the books are written in a language we do not understand. We slowly, painstakingly, decipher the alphabet, the grammar, the syntax, and begin to read the stories that nature has written. This image captures the essence of our quest for knowledge. It is a quest born of humility, curiosity, and a sense of wonder. At the end of our journey, we are left with more questions than answers. The boundaries of our knowledge have expanded, but so has the shoreline of our ignorance. But perhaps it is in the questions themselves, in our insatiable desire to understand, that our true significance lies. The next time you look up at the night sky, remember that you are not just an observer of the cosmos, but an integral part of it, in your eyes, which observe the stars. The universe is looking at itself and contemplating its own existence. In that moment of connection, in that flash of self-awareness, the infinitely large meets the infinitely small, the objective universe meets the subjective mind, and the great cosmic story finds its voice.